Welcome back to Wood Engineering. I'm Jeff Orochko from Carleton University, and in this video, we're going to start talking about design of bolted and doweled connections. I mean, mostly we're going to focus on bolts, but bolts and dowel design is basically the same thing. We talked about the difference between dowels and bolts in a previous video. So these are all the different parts of a bolted connection. I have the two pieces of wood here, and they are connected together by one bolt. So this is just happens to be a 2-member connection. We can do 3-member connections obviously as well. And you see that we have a bolt. The bolt has a washer on either side and a head and a nut. And maybe it's a bit clearer if I just show what an actual bolt looks like. So here's a type of bolt that we might use for connecting timber members together. This is I think it's a 1/2-inch bolt. Might be a little bit bigger. Anyway, so this is the essence of the connection, right? Is we're going to have a head on one side, and then on the bottom, in order to connect everything together, we screw on the nut. Both sides get a washer, and you can see that the thread is not along the entire length of the bolt, because usually what we want is we want the shear in the bolt to be happening on the shank, because in order to put on the nut, we have to cut these threads. The process of cutting the threads actually reduces the cross-section of the bolt at that point. So that's why we don't typically thread the entire bolt, because it's much stronger to have the shear occur here. Now in steel connections, you'll recall that if the thread is intercepted by the shear plane, we apply a reduction factor. There's no explicit reduction factor like that for bolted connections in wood. And the reason is because we don't typically shear we don't typically actually shear the bolts in wood connections, because the wood is not strong enough basically to shear the steel. So mostly what we have actually is bolt bending, and that will be less, then the area of the thread will be less critical. So that's what the bolt looks like. Inside the connection, looks like this. Here's my bolt again. One thing that you need to be aware of, which we have talked about briefly before, is that when we cut a hole for a bolt in timber, we have to cut the hole a little bit bigger than the shaft of the bolt so that we can fit everything together. So that means when I calculate net areas for wood members, and when I do my group tear out failure modes that we're going to talk about today, I need to take into account the fact that the hole is actually bigger than the bolt. So I have to take out the size of the hole when I'm calculating net area, not the size of the bolt. And in the standard, it says that the hole should be 1 to 2 millimeters bigger than the fastener. And so therefore, for design, we should consider that basically the worst case, that the bolt hole is 2 millimeters bigger than the bolt diameter itself. Okay, so we are going to be talking about a whole bunch of failure modes. The difference between bolted connections and nailed connections is that we have a whole bunch more failure modes that we need to check in design. So we still have the yielding failure mode that we had before for nails, and it's more or less exactly the same. There's a few minor differences between the two approaches, and that's from the Johansen yield equations that we talked about before. And in addition to that, we have some other failure modes that are non-ductile failure modes that have to do with failure of the wood. Okay, so there are 5 different failure modes that we need to check for bolted connections, unlike in nailed connections where we only basically had to check the one, which was yielding. So we have yielding, row shear, group tear out, net tension, and splitting. And these are also split into directions. So just like for nails, I can calculate yielding strength for any direction that the bolt is going. So if the bolt is going parallel to grain, perpendicular to grain, at an angle to grain, I can figure out what is the yielding strength of that connection. Now, unlike nails for bolts, the embedment strength, perpendicular to grain and parallel to grain, is a bit different, but we take that into account inside the yielding calculation. And so that one is any angle to grain, and it happens also to be the only ductile failure mode. So that means a failure mode where once we reach the limit in strength, we don't immediately have complete failure of the connection. So we have yielding, which means that the bolt will continue to bend, the embedment of the wood will continue to fail up to pretty large displacements. So we have some warning before we have failure of the connection, basically, because it takes some time to fail. Then we have 3 parallel to grain failure modes, which we're going to talk about in detail. And if you have done the steel design course, then you will be aware already of row shear and group tear out. We've already covered net tension failure when we covered tension strength of members. So that is basically the same thing as it was before. Row shear is pulling out a plug. So basically I push a plug of wood out the top. Group tear out is I take a whole chunk out of the piece of wood, and net tension is basically I fail across the full cross section of the piece of wood. So these are similar in style to what you see in steel design, but a little bit different because the strength of wood is obviously a bit different because the mechanics of wood are different. Reason being because wood is an orthotropic material, so we have weak planes due to the lignin joints that are holding the fibers together. So those are the parallel to grain failure modes, and then we have a perpendicular to grain failure mode, which is if I have my my bolt like this and I'm pulling down, which means I'm pulling my wood across in the tension perpendicular to grain direction, which we have talked about at length as being generally a pretty bad idea if you can avoid doing perpendicular to grain stresses, because it's the absolute weakest way that you can load a piece of wood. So this is the only perpendicular to grain strength check that we have in the standard for bolted connections for wood, and it is very weak, and we're going to see how to do that. So all of those B through E, all of those kind of wood failure modes, which don't have anything to do with the strength of the bolt, those are all non-ductile failure modes, because when wood fails and pulls out a plug or pulls out a chunk or fails across the cross section or splits perpendicular to grain, those are immediate failures. They're non-ductile. There's no displacement associated with those after you reach the failure point. So once you reach that failure strength, basically your connection breaks immediately. So for that means they're not very desirable failure modes. And so, ideally, I would like to design my piece of wood to use yielding as a failure mode, if at all possible, in my connection, and we will see a bit how we can massage our connection to do that. But the standard just gives you these strengths, so the strengths apply one way or the other. So I could have another one of these failure modes governing that's not yielding, but then I should be aware that it's not going to be ductile failure. Okay, so before we talk about the details, we are going to talk about the spacing requirements for bolts. Okay, so the spacing requirements differ depending on the direction of my load. So if my load is parallel to grain, I have one set of spacing requirements. If the load on the bolts is perpendicular to grain, then I have a different set of spacing requirements. So here I have my piece of wood and I have my bolt, and the bolt is either pushing towards the end or pushing towards the center of the piece. So if the bolt wants to move this way or the bolt wants to move this way, that's what we're talking about. In the standard, they have different figures for tension versus compression. I have tried to combine these together into one kind of summary figure, and but refer basically to the figure in the standard, which I've referenced up there. Now, one thing is that between the 08614 standard and the 08619 standard, the parameters for these have changed. So I'm also going to include both there. Okay, so we talked before about what are rows and what are columns. In this case, the rows are like this, right? In that direction, because the rows are the lines parallel to the loading direction, right? These ones would be the columns in this case. So in 08614, the labels for these spacings are in terms of rows and columns. 08619 makes, I think, a positive change, which is just to specify them either as parallel to grain or perpendicular to grain because it prevents you from having to determine which way the rows go. But that's not the case in 14. So let's look at this first, which is the spacing of bolts within a row from each other. Okay, and this one in 08614 is called SR for the within row spacing, or in 08619 it's called SP, which is spacing parallel to grain. So SR or SP. So you notice that the requirement hasn't changed. It's still 4 times the bolt diameter is the required spacing parallel to grain, but it's just that the parameter has changed, like what the parameter is labeled has changed. Okay, so that's row spacing. What about spacing between the rows, which in 08614 is called SC, which is basically the spacing within the column, and or SQ, which is spacing perpendicular to grain for 08619. Okay, so that's a less stringent spacing requirement of 3 df. Reasons are the same as why the spacing is less stringent for spacing perpendicular in nails. We talked about why that was. Okay, then we have our edge spacing here. Okay, so this is an unloaded edge distance because the bolts are not going towards the edge, either edge. So that is EP, the unloaded edge distance, and it is the maximum of one of 2 values, either 1.5 times the fastener diameter, the bolt diameter, or half of the perpendicular to grain spacing. Okay, and I say SC or SQ because it depends on which standard you're using for what the actual symbol for that is. Okay, and then the last one, this is the end distance, and whether it's loaded or unloaded end depends on which way the load is going. So it's not AL or A because of a difference between 08614 or 08619. It's because AL is the loaded end distance and A is the unloaded end distance. And we had the same, remember we had some of the same parameters for this for nailed connections, at least under 08619, where they changed the nail convention variable names so that they matched up better with these ones. Okay, so A. Okay, A is the unloaded end distance. That's what happens when we have the piece of wood that looks like this, and we have our bolt, and the loads are such that I'm pushing on the piece of wood and the bolt is pushing back. And so the end over here, the bolt is pushing away from it. So this is then going to be A, our unloaded end distance. Then we have AL, which is our loaded end distance, has a more stringent requirement of 5 df. So we want to be farther away from the end when we're pulling the bolt towards it, which makes sense. And it's the greater of 5 df or 50 millimeters. So whichever one of those is bigger, that's going to be my requirement for AL. And that looks like this. So if I have my piece of wood, and this is when I'm pulling on the connection on the piece of wood in tension. And so now my bolt in the piece of wood would be pulling towards the end of the piece. And so that's when this distance here becomes AL, the loaded end distance. So that's a summary of all of the spacing requirements when the load is parallel to grain. So then what about if the load is perpendicular to grain? Okay, so in this case, the load is perpendicular to grain, so the bolts are going to be trying to move up and down, up or down. So if I'm holding the bolt steady and the connection is moving, the bolt is either going to move down or the bolt is going to try to push up. Okay, so we have different spacing requirements for these. And they're going to look like this. So again, the parameter names are a bit different for 086, 14, or 19, but the requirements are identical. Okay, so let's look at spacing parallel. So as before, this was SR because it was the in-row spacing. Now it's SC because now these are the columns. Because this is the in-column spacing. Because now these are the rows. Because the direction of the load is like this, right? So then the rows are the same in the direction of the load. So SC is the within column spacing. So you can see why they've changed this, because SP, just making it the parallel to grain spacing, is a lot easier to suss out. Okay, so this here, spacing parallel. Another nice thing that they did in the new standard is that they actually put all these requirements in a table. Before, you had to kind of read them in paragraphs to figure out what they were. So now it's a lot more clear. So spacing parallel here now is only 3df, where it was 4df before, and that's because the load is not going parallel to grain anymore. So that spacing distance becomes less important. Then we have our spacing perpendicular. Okay, which is also happens to be 3df now. So for load perpendicular to grain, all of the spacing requirements between the bolts are 3df. Then we have our end distance. Okay, so this is always an unloaded end distance because the bolts want to go either down like this or up like this in these cases. So they're not going towards the end of the member. I say if close to the end because a lot of times if I have load perpendicular to grain, I'm in the middle of the piece of wood. I'm not necessarily near an end. So maybe this piece of wood goes off this way and off this way, and I'm just dealing with a connection that's somewhere in the middle. So I'm very far from either end. Which is, you know, totally common that could happen. So if I need to consider that end distance, then that's what the requirement is. Again, a max of 2, 4df, or 50 millimeters. And then the last one here is that we have our edge distances. And now our edge distances here depend on which way the load is going. This is going to be either EP or EQ, which is going to be our loaded edge distance or our unloaded edge distance. Okay, and that depends on which way the load is going. So let's look at that. So okay, so the requirement for spacing for the edge distance is greater. I need a greater spacing if I'm going, if I'm looking at the side that is loaded, the edge that's loaded versus unloaded. So if this bolt is trying to push down out of this member, then the loaded edge distance is the bottom distance here, which is the distance between the bolt and the loaded edge. That is the edge that the bolt will want to move towards in the connection. Then the unloaded edge distance will be this top distance here. And it's more important that I'm far away from the loaded edge than it is that I'm far away from the unloaded edge. So if I'm looking at these two cases a bit more pictorially, like this, okay, in the case that my bolt is trying to push down, then the bottom one will be my EQ, which is my loaded edge distance, and the top one will be my EP, which is my unloaded edge distance. That's because this is loaded and this edge is unloaded. Okay, and you know, the shear on the beam would look like this. Now in the reverse case where the bolt is pushing up, you know, and the shear is pushing down, then now my top edge is the loaded edge and my bottom edge is the unloaded edge. And so my EP and EQ are going to switch, and the top distance will be my EQ and the bottom distance will be my EP. Now, of course, this is for the last bolt in the connection, the one that's closest to the edge. that's what this distance is. You know, I've shown it here just for one bolt. If I had a bunch of bolts, you know, if I had a bunch of bolts, let's look at one of these cases. If I had a bunch of bolts and they're all pushing down like this, then my bottom edge here is going to be my loaded edge. So that's going to be my EQ. And the top distance here for the unloaded edge is going to be my EP. And then obviously in between the bolts, I have my perpendicular to grain spacing requirement. Okay, so that's how spacing works in bolted connections. So we've done a bit of an introduction and talked about all of the different failure modes that are possible and looked at the bolt spacing requirements. And now in the next video, we're going to start by talking about yielding failure modes.